Morning, which is by Wen Yuan, and the title is Embedding and Continuity Envelopes of Besov-type spaces.
Thank you. First, I would like to thank the organizer for their kind invitation and also give me such an opportunity to give a talk here. I also want to talk something about Besov-type space, which Winfried have already introduced something. But we are focused on the embedding properties and some of their applications. So this talk is based on some joint work with Dorothy Halowski, Susanna Mola, Lizzie Chak, and Dachun Yang. So in the first part, I would like to record all the function space we are dealing with, include the classical Besov-Triebel-Lizorkin space and the Besov-Triebel-Lizorkin space built on Morley space and the Besov-tau space. And later I will record some non-embedding properties of Morley smoothness. Then the third part and the first part is our main results. So the function space we dealing with are all introduced. We use the definition is by Fourier analytic approach. So this definition are somehow well known. We let phi j is phi j is a sequence of Schwarz functions such that their Fourier transform forms a smooth dialectical decomposition of unity on Rn. Then the Besov space BSPQ and Triebel-Lizorkin space FSPQ are defined in this way. So, as Winfried introduced in his talk, there is some new function space to generalize the Besov space and Triebel-Lizorkin space by using Morley space instead of Lebesgue space. So the idea is very simple. We just replace the LP norm in this in a classical Besov and Triebel-Lizorkin space by the Morley norm. So this space are the Besov-Morley space are introduced by Kozono and Yamazaki when they dealing with PD problem, and also Mazzucato in 2003. The Triebel-Lizorkin Morley space was later introduced by Tang and Xu in 2005, and later also by Sawano and Tanaka, and also Zico, Yang, and me. So the definition is not complicated, but these two spaces have some very different behaviors, like to comparing with the classical Besov and Triebel-Lizorkin space. Maybe one main difference is this one. If U is not equal to P, this means that these two spaces does not go back to the classical Besov and Triebel-Lizorkin space. Then we know that the Schwarz function is not dense in this function space. So this means that many density argument fails for this function space. Also, like some embedding properties, this is also a very trivial embedding properties for Besov and Triebel-Lizorkin space. But for the Morley type space, there is some different case, especially in this case, the parameter here Q is not the maximum of P and Q. It should be infinite. It cannot be improved. So from this we can there is some difference. Besides this Besov-Morley type space, there is another two kind of generalized Besov space and Triebel-Lizorkin space we call tau space. These spaces are related to another function space Q space I will introduce later. So we can see their definition. The Besov-tau space BS tau PQ. So we have a new parameter tau here. It's defined like this way. So first the integral is taken over a dyadic cube P, and the summation is not from 0 and from the maximum of the level of dyadic cube and 0. Then we over P tau. And finally, we take a supremum of all dyadic cube P. And also similarly, we can define the Triebel-Lizorkin tau space, just exchange the summation and integral. So this the base of tau space in when P and Q is greater or equal to 1 was introduced by L. Baraka in 2002. The homogeneous version, this is our inhomogeneous version, was introduced in 2010. The homogeneous version was introduced in 2008 and 2010 by us. As I mentioned before, the motivation to introduce these two scales is to connect, we try to connect the classical Besov space and Triebel-Lizorkin space to this kind of Q space, which original from complex analysis in the study of quasi-conformal mappings. And the real value of Q space was introduced in 2000 by these two persons. It's defined like this way by using the difference. Nowadays it's known that this Q space is a subspace of BMO. If alpha is strictly less than 0, it just coincides with BMO. We are also proof that this Q space are just a special case of Besov tau space and F tau space. And for the inhomogeneous case, we can show these results. The B tau space and F tau space in this special parameter just coincides with the intersection of Q space with a modified Morley type space. So here are the relation of this function space to some before some non-function space. So it's easy to see that if tau is equal to 0, then these two spaces go back to the classical case. So if we go back to the definition, if tau is 0, then this part just disappeared. Since we take a supremum, then here go back to the hope Rn, and here is go back to 0. So go back to classical case. And also, if tau is equal to 1 over P, a result by Fraser and Yavash, so means that this space coincides with Triebel-Lizorkin space in the limiting case P equal to infinite. Moreover, we also show that if tau is larger, if Q is less than infinity and tau is strictly greater than 1 over P, or if Q is infinity and tau is greater or equal to 1 over P, then we can show that these two tau space just coincides with Besov space in the limiting case P and Q both equal to infinity, but with a different smoothness. And also there has relations with Morley type space. We can show that the Triebel-Lizorkin Morley space actually coincides with some special Triebel-Lizorkin tau space. So this in particular, the Morley space is also a special case of this space. So this means that essentially for Triebel-Lizorkin spaces, the tau space and the Morley type space just coincide. But for the Besov-type space, Besov spaces, these are different. So only when Q equal to infinity, this space coincides with each other. But if Q is less than infinity and P is not equal to U, then the Besov-Morley space is a proper subspace of Besov tau space. So these spaces are different. So what we are interested in is about the embedding properties of this function space. So this means that we consider one scale from one Besov space or Triebel-Lizorkin space to another one, in which parameter we try to find the sufficient necessary parameter condition such that this embedding holds true. So on the for Besov space and Triebel-Lizorkin space, these results are already very clear. So first we see that this result is for Besov space. So for Besov embeddings between Besov space BS1 P1 Q1 to another BS2 P2 Q2, these are called some Sobolev type space. So nowadays it's known that this embedding is true if only if the integrity parameter P1 is less than P2, and the smoothness parameter satisfies this condition. So either S1 minus N over P1 is greater than S2 minus N over P2, or if they are equal, then we need an additional condition Q1 less than or equal to Q2. So this is a limiting case. In some sense, this is the most interesting case, most difficult case. And similarly, for Triebel-Lizorkin space, we have a similar condition. So we have also a condition on integrable parameter, another condition on the smoothness parameters. The third embeddings are the so-called Franka-Yavash type embedding, which is from Besov space to Triebel-Lizorkin space, or from Triebel-Lizorkin space to Besov space. So in this, we only list also only the limiting case, means that S minus N over P become a constant. In this case, it's known that such embeddings holds if and only if Q1 is less than P less than Q2. And also nowadays we know that all such embeddings, this Franka-Yavash embedding and also the previous Sobolev type embedding, are never compact because they are all defined on the hope Rn. So concerning the Morley smoothness space, the situation is also somehow very clear. It's considered by Harosky and Shipchak during 2012 and 2014. And also we first consider the Sobolev type embedding. For Besov Morley space, then such embedding properties hold true if only if we have these two inequalities is true. So now if we're comparing these results with the classical Besov condition, we can see that now the Morley parameter U in some sense replace the position of the integrable function P, because for Besov space the condition is P1 less than P2. But now for this Besov Morley space, it becomes U1 less than U2. But we have an additional condition P2 over U2 less than P1 over U1. And also for the smoothness parameter, we have a similar condition, just also replace P, parameter P, by the parameter U. And this is also if and only if condition. And for also similarly for the Triebel-Lizorkin Morley space, it has similar results. But for the Franka-Yavash embedding, the situation is still far from the very clearness. So they consider separate from Triebel-Lizorkin Morley space to Besov Morley space, and from Besov Morley space to Triebel-Lizorkin Morley space. Now they can only give some sufficient condition, and whether these conditions are necessary now is still not cleared. And it should also mention that the proof of these embeddings, one of the main tools is to use the wavelet decomposition of this function space. Then all these embeddings we can transfer to their sequence space, which is much more easy to handle. So of course, now it's very natural to ask how about the embedding properties for the tau space. And because we know that the f tau space coincides with the Triebel-Lizorkin space, and if tau is larger, both these spaces go back to the classical Besov space. So in some sense, the most interesting case, most unclear case is the Besov-type space with tau is less than or equal to 1 over p, which is also our main target. So, like the Besov space, we also need to use the wavelet decomposition of this function space. And the wavelet basis we used is a very good Dabshi wavelet, which you can have a very sufficient decayed moment condition. Then we define the lambda k and lambda ijk in the usual way. And also we need the corresponding sequence space related to this Besov tau space. So this is already introduced in wavelet talk. So here is what we need, the main two, the wavelet decomposition characterization of this Besov tau space. And this means that temporal distribution f belongs to this tau space if and only if it can be represented by this wavelet decomposition in the sense of the distributions with the related sequence space is sequence space known is finite. So from this there exists isometric from this function space with its sequence space. So when people consider embedding properties between this tau space, we can only need to consider the related embedding properties of the sequence space. So they are equivalent, and the later is of course more easy. So we can just because they are very concrete sequence space. So we can just have very detailed, very concrete estimate. So here now we can see our main results. The first results are Sobolev embeddings for this tau space. This means that we consider embeddings between Besov-type space, different Besov-type space. And also because there is a special number tau equal to 1 over p. If tau is larger than 1 over p, then they go back to Besov space. So we also separate these cases. So if the packed function space S2, tau2, P2, Q2 go back to the classical Besov space, this means that the tau2 is greater 1 over p, or when Q2 is equal to infinity and tau2 is equal to 1 over P2. So from in this case, we know that the task space is just the classical Besov space in the limiting case. So it's not easy, not difficult to show that this embedding is true if and only if these conditions hold true. S1 plus n tau 1 minus n over P1 is greater and equal to S2 condition. So comparing with the Besov space the condition, so we can see that there is an additional number n tau here. So if tau 1 is 0 and tau 2, you can go back to the classical case. So we can see that there is no need to add the condition on the P1. We don't need P1 less than or equal to P2. Conversely, if the starting space is go back to the classical Besov space, so we can also got a necessary and sufficient condition. The condition seems a little bit more complicated. So this embedding is true if and only if So we have the similar condition on the smoothness parameter, but we also have additional requirement on tau 2. We need tau 2 is also greater or equal to 1 over p2, or if is equal to 1 over p2, then we need q2 is equal to infinite. So because we know this means, from these results we know that this means that if the starting function space is limiting Besov space, then the touch space in some sense is also a limiting case, so a big space. So the most complicated is this case. Both tau 1 and tau 2 is small, is less than or equal to 1 over p. Then we have these results. The embedding is true if and only if this. First, we have a condition tau 2 minus tau 1 plus 1 over p1 plus minus 1 over p2 greater than or equal to 0, and tau 1 over p2 less than tau 2 over p1. Looks very complicated, but if both tau 1 and tau 2 are 0, then we can see that this condition just disappeared, and this condition is just p1 less than p2. So it just go back to the classical Besov case. And also the second one is for the condition for smoothness order. So in the limiting case, so we need some additional requirement on tau 1 over p2 comparing with tau 2 over p1. So we can also prove that all the red conditions are also necessary. So the only gap is this one. In this case, if in this limiting case, we need to additional requirement tau 1 over q2 less than tau 2 over q1. Of course, when tau 1, tau 2 are 0, this disappeared. But if tau 1, tau 2 are not 0, this condition exists. And we are not now it's still unclear whether we can also show these properties, these conditions are also necessary. So the only gap is this one. But if we consider some special case, we can got some interesting even only if condition. So like from the Besov space to Besov tau space, we can got a even only if parameter condition. Also from Besov tau space to Besov space also have some even only if conditions. So here maybe we should mention that if from tau space to Besov space, the condition we need that tau 1 over p2 is 0. So this means that either tau 1 is 0 or p2 is infinite. So so we cannot have such condition that tau 1 is large and q2 is small. We cannot have this. Most particularly is this one. We consider the condition when the Besov tau space embedded into a continuous function space. So it's also easy from the previous results. It's also easy to see that the Besov tau space embedded into this continuous bounded function space if and only if either S is strictly greater than n over p minus n tau, or in the limiting case S equal to this one, then we need tau is 0 and q is less than or equal to 1. So the later is just a classical result in the Besov space. And the last very quick corollary is this one. So not only BS tau PQ embedded into CRN, we can show that the condition for B tau space embedded into L infinite space and embedded into the uniformly continuous unbounded functions, all these parameter conditions are the same. So all such embeddings are equivalent. So these are results for soft-level embeddings, say from Besov space to another Besov-type space. So if we want to consider Franka-Yelves-type embedding, so this means from a Besov-tau space to a Triebel-Lizorkin-tau space, or conversely from a Triebel-Lizorkin-tau space to a Besov-tau space. So we have also a nearly sharp condition. Of course, now in this case, we also only need to consider the limiting case S1 plus N over P1 minus minus N over P1 plus N1. This number is a constant. So the embeddings from Besov-tau space to Triebel-Lizorkin-tau space, and from Triebel-Lizorkin-tau space embedded into Besov-tau space holds if tau1 and tau2 is equal, or if they are not equal, we need tau1 times P1 is strictly less than tau2 times P2. So we need such condition. And for these embeddings, the only unknown case is the limiting case tau1 P1 equal to tau2 P2. Whether in this case the embeddings are still true, because we can show that if here is a strict tau1 P1 is strictly greater than tau2 P2, then these embeddings are not true. So the only gap is the limiting case for this. So these are some embedding results behaviors of tau space. So finally we can use these embedding properties to consider the continuity envelopes in this tau space. So this is known that the continuity envelopes is introduced by Triebel in 2001, and also Harowski in later. So we need to define this notion. We need to use the modulo of continuity of a function omega ft. So if a function space X is embedded into continuous and bounded functions, then we can define the continuity envelope function abstract C, which is defined in this way. We take a function in f in this function space, and they consider its modulo of continuity over t. Then we take a supplement over the unit ball in this function space. This gives a function over t. So it's already proved by them that if X, this function space, is good enough, is embedded into a ellipsis space, then the envelope functions is bounded. So this means that the most interesting case is that X is not embedded into ellipsis space. So this means that the envelope function is unbounded. So in this case, when X is not into ellipsis function space, one can further define the continuous envelope like this way. So we need to use a number UCX, which is an infimum of all numbers nu, such that this integral can be controlled by the x norm of f. So from this definition, it's not difficult to see that the envelope functions measure the growth of a function in x in a quantity way. And the second one, this number UCX has gives some way to measure the integrability of this modulo of continuity of f. So this is also the motivation of Triebel to introduce these notions, and they have been these notions have also used to study some sharp and compact embeddings of Besov and Triebel-Lizorkin space. So we can record some classical results. So for the C function C, then the continuity envelope is equal to the envelope function is just t2 minus 1, and another number is infinite. And for Holder continuous functions, the envelope function is t2 alpha minus 1. For Besov space, the condition is nowadays is cleared. If S the smoothness is equal to N over P plus some sigma in between 0 and 1, then the continuous envelope of Besov space is equal to T2 tau sigma minus 1, and the other number is Q. And the Triebel-Lizorkin space a little bit different. The integral number is P. So in the limiting case, when S is equal to N over P plus 1, then there is a different, the envelope function becomes a log function in this special case. So we consider these results for Besov tau space as our embedding results shows before. We have already known that the Besov tau space embed into CRN if and only if S is strictly greater than N over P minus tau. And if S is embedded into ellipsis 1 space, if this means it's if and only if S is strictly greater than O, this number plus 1. So if we want to consider the continuous envelope of this function space, we need to consider the smoothness between these two numbers. So here is our results. If tau is greater than 0, then if S is in between these two numbers, its envelope function is this one, T2S plus N tau minus N over P plus 1. And if in the limiting case, S equal to N over P minus N tau plus 1, then we also have a log function here, log T. But the integrable number is infinite. So comparing with the Besov space, you can see that Besov space, the integral number is Q. So this means that between from tau equal to 0 to tau greater than 0, there is a jump of these two space in this continuous envelopes. So not a continuous. So finally, we can have some further applications. The first one is hard type inequalities related to the modulus of continuities of functions f in this tau space. So also we separate in limiting case and non-limiting case. So this gives some very quantity estimate of the modular of continuities of these elements f in this space. Another application is we can have some estimate of approximation numbers. So this number I think is somehow well known. If x, y are two Banach space and t is a bounded operator from x to y, then the case approximation number ak is defined as an infimum of this one. We use operator with rank smaller than k to approach the operator t. So final our last results, because it's known that the approximation number can be dominated by the continuity envelopes. So use our previous results on the estimate of continuity envelopes, we can finally got this one. If P is greater or equal to 2 and SE is between this range, then the approximation number of the embedding operator from B space into C omega, we can have a concrete estimate on this K2 this parameter. So if tau is equal to 0, this is already known in these papers. So I think I'll stop here. Thank you very much.
Any question?
Just to your last result on the approximation numbers. So you
Yes.
presented a result on embedding into L infinity or continuous functions. So maybe I missed that point. What was again the connection to the envelopes in that setting? Because it's often difficult to compute sharp results.
Yeah. I maybe I forgot to. That is an estimate. AKT AK ID is less than or equal to some positive constants times the continuous envelope functions. A general estimate. So if you have an estimate of envelope function, then you can go to this estimate of approximation numbers.
Okay, interesting.
More questions? So let's thank you.
Thank you.